This is the lesson for Friday or Thursday, February 3rd, that I forgot to record earlier during class. So for anybody who's not here, please watch this, take a look at it. It covers a little bit of what we did yesterday, which I didn't get a video on, and we will use this again in the next lesson. And then we'll spend a couple days practicing this with some labs starting Monday or Tuesday next week. So we talked about calorimetry last time. Okay? Calorimetry is basics of the energy that is gained or lost by the system goes only to the water or something measurable in the other calorimeter. So if I lose energy from the system, the calorimeter will gain the exact amount of energy that we lose. Is a calorimeter perfect? No, but it is a fairly good estimation that we can use for our calculations. It is based on this principle. The energy gained or lost by the calorimeter is equal to the energy gained or lost by the system. So we talked about Q a couple days ago. Q is equal to MC delta T, where M is mass, C is the specific heat, and delta T is your change in temperature. N, as we do in chemistry, N stands for the number of moles or the chemical amount, where delta RHM is your energy change per mole of whatever reaction is taking place. So per mole, that's the important part. And this here unit is in kilojoules per mole. And so here's an example. When 3.5 grams of ethanol is combusted in a sophisticated calorimeter, the temperature of 3.6 liters of water raises from 19.88 to 26.18. Now, I'm just going to get out of that and get into that. Okay. So, when I do these problems, I have my chemical system and I have my calorimeter. So, the calorimeter, we have the volume of the water is 3.63 liters. The delta T is 6.30 degrees Celsius, the difference between them. Now, I could definitely show specific heat capacities 4.19 joules per gram degrees Celsius. I just probably won't because that guy's in liters. So I'm going to, the nice thing about water, 4.19 stays the same. The units change. So everything on my calorimeter side, I record there, make my life a little easier. We have mass over here of 3.50 grams. It's ethanol. Quickly calculate the molar mass of ethanol. It's 46.08 grams per mole. What we're looking for is the heat of combustion per mole of your ethanol. Okay. So that's what we're looking for. So we start with this idea of the energy change of the system is equal to the energy gained or lost by the calorimeter water. Now, in this case, it just says water. If it was an aluminum cup, I might include something different in there. So, an M. And I'm, in this case, doing a little bit of work. Instead of doing this calculation beforehand, I'll throw it in here. I take my mass over my molar mass. So this is the mass of the ethanol. This is the mass of the water, or in this case, the volume. I guess I should put it with a V. We have our 3.63 liters, 4.19 kilojoules per liter degrees Celsius times 6.3 Celsius over and now from here it's just a calculator question. Once you get everything plugged in, calorimetry, or once you get everything in the right place, calorimetry is not that difficult. We end up with and the units, the liters go away, the degrees Celsius goes away, the grams go away, and we end up with kilojoules per mole. And we have a significant digit issue. I'm going to write this as 1.26 megajoules per mole because of my three significant digits as controlled by my temperature and this one and that one. And now the temperature went up from 19 to 26. So that means that this chemical system gave off energy to heat the water up. That means the system is exothermic, and we indicate an exothermic reaction by a negative sign. I think of it this way, energy leaving the system. Back to playing with this. Okay. So next question. I already talked about that. We already mentioned that. Next question. Determine the final temperature of a calorimeter containing 3.63 liters at 21.25 Celsius if 3.5 grams of octane is burnt in the combustion chamber, and I'm giving you the molar enthalpy of the solution. So per mole of octane, 5,400 joules of energy, kilojoules of energy gets released. So again, same thing that I'm going to do. I've got the system and I've got the calorimeter. So delta T is what we're looking for. We are given T, the initial temperature, which I'll abbreviate TI. I'm not going to use that until the end. We have, again, our volume is 3.63 liters. So I will use the 4.19 kilojoules per liter degrees Celsius. If you use this 4.19 joule per gram degree Celsius, you would just have to make sure that the 6.3 liters gets turned into grams. So 3.63 kilograms, 3,630 grams. Our system, again, our mass is 3.50 grams. Quickly do our molar mass, which for some reason I have memorized. Is 114.26, and we're looking for the heat of combustion here. So again, starting with this idea of the overall energy change of the system is equal to the energy change that happens in the calorimeter. So N delta RHM over MC, that is our change in temperature. I'm not using that until the end. So quick little calculation for this one. For the molar mass, I'll just do that in my head or on my calculator to start with. And so we have 0.306 moles times our, we're not looking for that. We are given that. This was negative 5470.1 kilojoules per mole. And that's overall equal to your delta T. So I'm just going to check to make sure everything crosses off. Those moles will cancel, those kilojoules will cancel, these liters will cancel, leaving me with 1 over 1 degree Celsius. So that's your degree Celsius, that's a good thing. Now it's just a question of plugging that in. Don't plug that negative sign. I don't know why I put it there. Again, I'll talk about that negative sign in a second. I get a delta T of 11.0 grams, or degrees Celsius. 3 significant, 3 significant. So my overall energy change is 11 degrees Celsius. The negative sign here tells me that this is an exothermic reaction. So an exothermic reaction is going to release heat to the environment, and your environment will get warmer. So your final temperature will be the initial, which was 21.25, plus your 11. So we have 32.3 degrees Celsius due to our rules of adding significant digits. And, okay, so I'll just skip that one. So those are a couple of examples. Hopefully you caught on to that. And I will go over some more examples in tomorrow's lesson.